Okay, so this is part two of the Renewable Energy Technology course lecture on hydropower. And when we left off last time, we were doing a case study of Oakland Mills, which is 400 square miles of drainage located, and that's the drainage area of the watershed, located between Fairfield and Mount Pleasant, about 15 miles from the classroom. The head is 8 feet. Let's assume that's we can get 8 feet if we repair the dam there. You can look, maybe it's not quite, whoops, let's see, where is it right there? Okay, you can see that maybe it's not quite 8 feet there, but we could get 8 feet, let's say. And then the flow. So now we need to figure out the flow. And what we need to do is we need to have some long-term averages of flow if possible, because we know the flow in the river will vary from year to year. And so we want to get an idea over time how much energy we can produce so that we can see if this thing will pay for itself or create us a profit if we're doing this for as a business. So one of the things I discovered is that flow records are not readily available for the Skunk River at Oakland Mills, which is 401 square miles. But they are readily available for the Skunk River at Augusta, which is just a little further downstream, and that's 4,300 square miles. So we can just adjust the figures for Oakland, for the Skunk River at Augusta for Oakland Mills by using the ratio of the drainage areas of 4,000 to 4,300. And in this case, for this example, we're just going to use the numbers at Augusta, at Skunk River at Augusta, and it'll be a little overstated. So let's take a look at these flow records and see what they look like. We'll see what I'll show you the what I got. So here's this is this book I found from the USGS that has the Skunk River at Augusta, Iowa, and it shows the location where the gauging station is, the drainage area, 4,300 square miles. The period goes from 1913 to 1996, so we've got some really good long water data that we can use to analyze this project. The gauge is it's a little bit about the gauge, and it tells you a little bit about the extreme. So the maximum discharge that's been seen is this 66,800 cubic feet per second, and the minimum is 7 cubic feet per second. So that's a huge difference, right? Huge difference in the amount of flow that's available. But those are very rare events. Those don't happen very often, so we can sort of ignore them. Then let's look at, this is how the gauging station works. So what this shows is that the height of water on the gauge, this indicates how much flow in cubic feet per second there is in the stream. And somebody had to go out and sort of calculate this and calibrate the amount of height of water in the river to the amount of flow in the river. And you can see that this has been done. And then if you look at, here's some monthly mean and annual mean discharges. So you can look at that the, for all the different months, the maximum, the minimum, and the average for every different month. So the average is about 2560 cubic feet per second for the mean or average flow. And you can see how it varies from month to month. And you can see it's got a peak in March, April, May, and June, and then it goes quickly to a minimum in looks like August, September, October, November, in December are the minimum flow times, and it looks like a ratio of about 3 to 1, 2.5 to 1, 3 to 1 between the best months and the worst months. And this shows the this is the mean annual discharge right here. And this is the annual mean discharge for all the different years. So this is how it varies from year to year. Before it was showing you month to month on average, and this is year to year. So you can see some years the average discharge quite high, some years it's quite a bit lower, but this is the average. And this is the 50th percentile. I mean, half the years are more and half the years are less than this amount here. So then from the USGS has also developed a flow duration curve. And what this we talked about these earlier, but what this says is, just to give you an example, 5% of the time the flow is 10,600 cubic feet or greater on an annual basis. And up to 85% of the time, 99% of the time, the flow is 30 cubic feet per second or more. And so you can just see the flow duration information here for the whole year and for each month. And this is what we use to calculate our power. And what else we got here? This is the magnitude and frequency of low discharges. Okay, this is, yeah, that's not too useful to us there. And so then that's kind of just what the raw data looks like. So let's go back to the PowerPoint. And so one place to start is to design for the average flow, which is about, we said, was about 2,600 cubic feet per second, and assume 90% efficiency for the turbine. So in that case, what would be the output of the machine? It would be the efficiency times the head in feet times the flow in cubic feet per second divided by 11.8. So if I plug all those numbers in, I get 1,500 kilowatts is what's going to be the output of this machine at its rated that we're going to install there. So let's look at a little bit more about what that means. Does that mean it puts out 1,500 kilowatts all the time, or it only puts out 1,500 kilowatts? Let's look at that. So first we'd have to select our turbine, and in this case, we're going to have about 8 feet of head, so we're going to be in the area of a cross-flow or a Kaplan turbine. Kaplan turbine, let's pick one of those. It's a propeller type turbine. I know that'll work well here. And then let's take a look at what the characteristics of the Kaplan turbine are at part flow. So this shows the efficiency at various percentages of the rated flow of the machine. So the red line is a propeller type turbine, and this one represents the full rated flow, in this case 2,600 cubic feet per second. And then you can see that all the way down to 0.3 of its rated flow, or 0.3 times 2,600, it puts out over 80% efficiency. So that's pretty good. And so we can follow the flow of this river quite well with one of these Kaplan turbines. And if we put 2 of them, we could do even better. Even at 10% of its rated flow, or 260 cubic feet per second, it still is 50% efficient. So we can operate this turbine for quite a long time. So we'll choose a Kaplan propeller type turbine. Has a good efficiency from about 0.3 of the rated flow to 1.1 of the rated flow, 85 to 90%. So what's it going to operate? It's going to operate down to 260 cubic feet per second and up to 2860. And at 260 cubic feet per second, it's only going to have 50% efficiency. But it's going to have, at 780 to 2860 cubic feet per second, it's going to be between 85 and 90% efficient. So that's probably a pretty good turbine for this. Now here's the data for the Skunk River. And you see that we've got, so if we want to look here at what was our minimum flow that's going to operate is 260 cubic feet per second. So you look, we could go down to the 80 percentile. So we could operate 80% of the time, there's 290 cubic feet per second or more, okay? And so then we go up to, the maximum amount was 2860. So we go up here 2840. So 25% of the time, there's 2840. So it's going to operate 25% of the time, there's 2840 or more. If there's more, we'll just spill it over the dam. There'll be 2840 going through the turbine, and the rest of it will spill over the top of the dam. So 25% of the time, we're going to be operating at 2840 cubic feet per second. So, so how do we figure out how much this turbine's going to run? So the minimum amount, so it's going to 80% of the time it'll run at least 260 cubic feet per second, and 25% of the time it'll run as much as 2840. Now that means excess water is available that we're not going to be able to use, because 25% of the time there's more water. So that means for about 90 days of the year we'll be spilling water over the dam because the turbine isn't big enough. But it's really not practical to put in a turbine that'll use the amount of water just in those few days when there's extra. So this probably works pretty good. Let's take a look at it. So then what I did is put together a spreadsheet, and I put together assume that there's 8 feet of head, and I put together the flow duration curve points. So at the 25% of the time flow equal or exceeded, it's 2840. All the way down to 80%, it's 290. And these are all the different points in between. Again, that just came off this graph here, off these numbers right here. And then I plug in the turbine efficiency because remember my turbine is efficient from 2840, it's 85% all the way down to about 400 cubic feet per second. And then it drops off at 290, it's only 50% efficient. And again, I used, I'll show you the curve I used to determine that. I used this curve, and so I can see at what percentage of the full flow the efficiency is of the turbine. And then I just plug in the formula for power output. The head times so the head's 8 feet times the flow times the turbine efficiency divided by 11.8, and that's the kilowatts it'll produce at each of these flow rates. So here's where the kind of magic comes in. So how many hours is it going to operate at that flow rate? Well, at the maximum flow rate, 2840, we know it's going to operate at least there's that much 25% of there's that much flow or more 25% of the time. So we know it's going to run 25% of the year, which is 8,760 hours in a year times 21 times excuse me 25% of that gives us 2190 hours. And so what's the kilowatt hours? It's going to be the output, 1733 kilowatts, times the power times the hours is going to give us the kilowatt hours. So we're going to give about almost 4 million kilowatt hours when it's running at full output. And then now let's look at 30% of the time, it's 2,300 excuse me, cubic feet per second. And then when I run the numbers on that, it's 1,400 kilowatts. And how many hours is it going to run at 1,400? Well, it's going to run at the difference between 30% and 25%, or 5% of the time, it's going to run at 1,400 kilowatts. So I just 5% of 8,760 hours, and I just throw that in there, and I get my kilowatt hours. Okay. Now the next one, it's going to run at 1,500 kilowatts, and how many hours can it run at 1,500 kilowatts? Well, the difference between 30 and 40%, which is 10% of 8,760 hours, is 876 hours. And that's the number of kilowatt hours I'd get there. So, go down through here with all the different points on the flow duration curve, and I get 6,529,000 kilowatt hours. Now, if I got 8 cents a kilowatt hour, now we pay about 15 cents, so that'd be half of what we pay. I'd make about $500,000 a year. And the cost to build that plant, let's say it'll be between $1,000 and $2,000 per kilowatt, but let's say $2,000 per kilowatt for a 1,700. I think I used the wrong number there. That's wrong because I used 2840. It should be 1,700. So that'll be, let's just go calculate that really quickly. 1733 times, let's see. Just a second here. Well, we might be able to just estimate it. Let's go back and take a look at it. So, if we multiply 1733 times 2,000, 1,700 times 2,000 would be 3,400,000. It's going to be around $3.5 million rather than 5.6 because I made a mistake here. I multiplied the flow times $2,000, not the kilowatts times $2,000. So $3.5 million. So roughly 6 years, rough payback, it would pay itself back. And now you throw some expenses in there, maybe 10 years, it'd pay itself back. And then for the next 100 years, it'll produce power. So it'll produce power at and continue to be a very lucrative project. So there's two pieces missing here. Hold on just a second. Let me look. Got the wrong wind energy tech. Okay. So now I wanted to point out ways in which these energy systems start to interact. In other words, what if you've got wind? What if you've got hydro? What if you've got a network that has all of that in it? And here's a little story from Denmark. You know, we've all heard how much wind power and renewable energy Denmark has and how much it's committed to. So much power was produced by Denmark's wind farms on Thursday that the country was able to meet its domestic electricity demand and export power to Norway, Germany, and Sweden. On an unusual windy day, Denmark found itself producing 116% of its national electricity needs from wind turbines yesterday evening. By 3 a.m. on Friday, when electricity demand dropped, that figure had risen to 140%. So it's producing all the energy Denmark needed just from wind turbines. And Denmark also has solar panels, and it also has biomass, and it also has cogeneration plants that had risen to 140%. So interconnectors allow 80% of the surplus power to be shared equally between Germany and Norway, which can store it in hydropower for later use. So how do they store it in hydropower? Well, what they do is, if they've got extra wind power, they just back off on the setting on their hydro turbines and use less water. What happens to that water? It stays in the pond above the turbine and is available for use later. So in a way, what they can do is they can store this wind energy in water that they don't use, that they'll have available to use later. And it shows that a world powered 100% by renewable energy is no fantasy, said Oliver Joy, a spokesperson for the trade body of the European Wind Energy Association. Wind energy and renewables can be a solution to decarbonization and also a security of supply at times of high demand, because when you have high demand, you can just call on that stored water. So let's take a look at this, this website. I'm pretty sure this is going to take us there. Hold on. And what this shows is it shows we're having trouble, hopefully. There we go. And let me see if I can capture that. No, it doesn't look like it can. So I'm not going to worry about it now. So So I wanted to show you an example of this happening in, there. So what that shows, the Ludington Pump Storage Facility, which is in Ludington, Michigan, on Lake Michigan. And you can see what happens here is when there's surplus power on the grid, there are turbines that actually operate as pumps, and they pump water up to this reservoir. And then when the grid needs power, they run the water back down through these devices, and in the opposite way, they actually act as turbines. So they can be either turbines or pumps. And here's what it looks like in real life. And this has been around, I think since the 70s, and it produces as much as 1,872 megawatts, which is as much as a couple of large coal-fired power plants, enough for 1.4 million homes. So we already have pump storage, and we could do more of it. And then we're going to close with this little video clip from Wyoming on water power.
To many Wyomingites, hydropower conjures up images of giant dams on the North Platte or Wind River, but hydropower comes in many sizes. Small hydropower, where a system produces enough electricity from 1 to several hundred homes, is seeing increased interest.
Here at the municipally owned Buffalo Hydroelectric Facility, raw water is diverted from Clear Creek on its way to the water treatment plant. The town of Buffalo cost-effectively installed a hydroelectric turbine to reduce pressure before the water enters the treatment plant. The amount of energy that can be extracted from water depends upon the head, which is the elevation the water falls, and the flow, or the amount of water. The Buffalo facility has a capacity of 225 kilowatts, which powers nearly 200 typical homes. The average flow of 6.3 cubic feet per second falls the equivalent of 530 vertical feet. Other entities across Wyoming also use small hydro. Lower Valley Energy, a rural electric cooperative in the western part of the state, operates 2 small hydroelectric facilities. New small hydroelectric systems are being considered at places where water infrastructure already exists, meaning no new dams.
Wyoming's working waters can do more than just provide a cold drink or irrigate alfalfa. Many can also produce a significant amount of electricity. From the University of Wyoming Extension, I'm Milton Geiger, exploring the nature of Wyoming.
Okay, that's it.